physicist, a theoretical physicist. I have been trained in statistical physics, statistical mechanics, and from my PhD I applied statistical mechanics to geophysical fluid dynamics and geophysical fluid turbulence. Initially I was explaining the self-organization of planetary scale phenomena like jets and vortices. So it was directly connected to climate. So the aim of my work has always been to develop new tools in statistical physics and in mechanics for climate sciences. But recently, since maybe for about 10 years, I decided to move towards more applied things, given the urgency of attenuating climate change and mitigation. So today I will try to show you a few examples where statistical physics can be useful for climate sciences. There will be a theoretical part, like a theoretical physicist, but there will be also very applied things to study extreme events and the extreme of renewable energy production. So I want to thank my collaborators. You see their name here. Most of them were working with me at INS de Lyon. So I recently moved from INS de Lyon to INS in Paris last year. So with some colleagues in France, we also built a few years ago what is called the Institute for Earth Planet, for the mathematics of Earth Planet, which is an interdisciplinary institute that aim at funding theoretical physicists and mathematicians when they want to touch with sciences which are related to environmental problems at large. So it includes climate, but it is much broader. It could include biology, the problem of biodiversity, health, and generally speaking, the environmental crisis. So I think there are many of these endeavors all over the world, and so I think this is something which is quite interesting, and lots of colleagues were interested to participate to this project. So this is the outline of my talk. So I will introduce rare events, which is my specialty actually, large deviation theory, which is the key tool from statistical mechanics for studying rare events, and rare event simulation, which is the tool from the point of view of computational sciences, which will be very useful for application. And as you will see, it also comes from statistical mechanics. So the theoretical part will be path large deviation for the kinetic theory of wave turbulence, and the application part will be the study of rare heat waves and extreme situation of renewable energy production. Actually, I will speak mainly about heat waves, just one slide about the renewable energy production. So this first slide is to insist on the fact that we are interested on extremely rare events. And so on this slide, you see during the last 25 years, the annual death by major climate-related disasters compiled by one of the UN agency. And so you see that there are three events: the Western European heat wave in 2003, the cyclone Nargis in Myanmar, and the Russian heat waves in 2010. And those three events, they completely dominate the statistics. They are very different from one from the other, and so they are in a different class of physical phenomena. So each of them is somehow unprecedented, and we don't have statistics. And so this is extremely important. So you see, it's not the tail of the distribution, but it's the far tail of the distribution. And so even if with climate change, when these events will become more probable, this is the events which are in the far tail of the distribution of the present climate that will be important. Because you have to multiply a very low probability with a huge impact. Okay, so we need to study extremely rare events, and so of course this is a serious scientific challenge. So for instance, here you see the example of the 2003 European heat wave. So there were 70,000 people dying on top of a usual number. So what you see is actually the temperature average during a month in July, August 2003. And so you see fluctuation of the order of 10 degrees. So 10 degrees, it is the order of the daily fluctuation for weather. But 10 degrees for a month average is something huge. It means that you had a moment with temperature much higher, and the fact that it had such an impact is related to the fact that it lasted long. So here it's a monthly event for dynamics, which typically have a mixing time of the order of a few days. After a few days, you lose the memory of the chaotic dynamics. And still, here it develops a coherent event that lasts something like a month. And so, as I said before, the scientific difficulty is the lack of observation data. We might use climate models, which are wonderful, and actually the science of climate model is an amazing part of contemporary sciences. So what climate model can do is really wonderful, but they are still far from being perfect. There are some biases, and especially for extreme events, it's hard to know what it's hard to benchmark them because of the lack of data. And there is a third point, is that even if the model would be perfect, because the event is so rare, gathering a good statistic would be too costly from the point of view of the numerical simulation. And this will be the point I will touch today. Okay, so this slide just summarizes exactly the same thing as before, these three problems. So we have a practical question, how to sample the probability and the dynamics of this rare event in complex model, and how to build effective models which are relevant for estimating the probability of rare events. So from a theoretical point of view, coming from statistical physics, I use large deviation theory. So I guess many of you know what is large deviation theory. It's a general framework to describe probability distribution in asymptotic limits. So for instance, you look at the probability that a random variable x is equal to x. This is just a PDF. So it depends on some parameter, physical parameter epsilon. And you look at asymptotically when epsilon is very small. So if you have, this means logarithm equivalence. It means that the log of the right-hand side is equivalent to the log of the left-hand side. And so if you have this factor, exponential minus f divided by epsilon, you call this a large deviation principle. And so this is at the core of statistical mechanics. For instance, for statistical equilibrium, f is just the entropy or the free energy, one of the free energies. And so it provides a mathematical and conceptual framework to study and understand rare events. And as you will see later, it is not limited to equilibrium statistical mechanics, but generally speaking, we apply this to dynamical phenomena independently of the equilibrium statistical mechanics. So the second key point is the computation side. And so here the practical question is how to study a 10,000-year heat wave, a heat wave that has a return time of 10,000 years. So you will see it once every 10,000 years in your model simulation, with if you can afford only a 200-year simulation. Okay, so it's a very classical question. So and the answer goes with what are called rare event simulation. And so the first algorithm to do that was developed by Kahn and Harris, following an idea by von Neumann. So it was in 1953 at Los Alamos. They were trying to compute the very low probability that a ray will go through a concrete wall related to nuclear application. And then they had an effective model, but they were not able to sample it directly, so they used this model. And then we have plenty of this algorithm in statistical mechanics, in statistical physics. That's where I learned it. And so what we did in my group, I mean, we studied the possibility to use this algorithm for turbulence and climate application for now more than 10 years. And so recently, several other groups in the United States, Jonathan Weir, Dorian Abbott, applied it also to climate, or Rainer Grauer and Tobias Grafke to turbulence, Eric van den Eyden to both climate and turbulence. And so there are now many groups all over the world that use this algorithm. And so I just want to give you one example of this algorithm. So what is important to understand is that there is a full family of them. Each of them is suited for a specific application. So here, the point, this is a sketch of a phase space. You have two attractors, A and B, or just two sets of the phase space. For instance, for me, A will be the typical fluctuation of my climate, and B will be the set where I have extreme heat waves. So I start from X, and most of the times I will go to the typical fluctuation. It is possible to go to B, but it is very rare. And so this is the point, how to get trajectory that goes from X to B rather than A, and how to estimate their probability. And so, for instance, we applied this to the van der Waals-Canillard model that describe phase separation, stochastic partial differential equation. And there, we were computing probability of the order of 10 to the minus 20. And we were able, for this case, because we know the statistical mechanics result, the Kramers formula, we were able to benchmark it from the theory and check that it is correct. So the way it works is like this. So you have to run an ensemble of trajectory. So here on the sketch you see 3 trajectories. Usually it's more like thousands or tens of thousands of trajectory in parallel. So you monitor how far you want in the direction of B with a function Q, which is called a score function. So you see here the trajectory 3 was the best, the trajectory 1 was the worst. So we delay the trajectory 1, and we take a new trajectory, the purple one here, that use the initial condition of one of the others taken randomly on the same level line as the maximum that was reached by the trajectory 1. And then we make a new trajectory. So the new ensemble, 2, 3, and purple, is better than the initial one. So we are progressing as an ensemble of trajectory in the direction of B. So we have chosen n-1 trajectory among n, so we can estimate the probability of this new ensemble to be 1 minus 1 over n, n-1 divided by n. And so then we do this recursively k time, and so we have very efficiently lots of trajectory that go through and reach B, and we can estimate their probability. So this is one example for which we very efficiently estimate the probability of an extremely rare event. So here, there is a crux. I mean, here you use a function Q to make your selection. So your function Q has to be good. If it is not good, the algorithm will fail completely. Okay, so then there is a whole application science side on this, how to choose this trajectory, how to do this with machine learning, and so on and so forth. So I will not go into this detail, but this occupies us a lot to solve this practical question. Okay, so let me go now to some application related to climate sciences. Alors, the first application will be wave turbulence. So you see here a wonderful picture. So we'll be interested in waves over the ocean. So you see here the scale where the wave breaks. So it is at the wavelength scale. So you have a wonderful picture. So it is very wonderful. It's probably the science some of you like to do, but that's not my interest for climate application. For climate application, we will want to change scale and to look at waves at a larger scale. And so here you see a wave field at a scale which is slightly larger. So you see tens of wavelengths, and so tens or hundreds of wavelengths. And so for me, this will be the microscopic scale, actually, the wave field at this scale. I will do statistical mechanics for which this is the microscopic scale. And then the mesoscopic scale or the macroscopic scale will be the description of the wave packet at the scale of one ocean. So for instance, here you see a simulation where what is shown is what is called the significant wave height. It means that 1/3 of the waves have a height larger than HS. And so here the green value is about 10 meters. Green-yellow is about 10 meters. So here you have 1/3 of the waves that have a height larger than 10 meters. Okay, so you see, I will show you a movie. And so this movie comes from simulation that goes along with weather simulation. So this is done operationally by weather centers, where you see the evolution of the weight field at a global scale. And so this is forced by the wind, of course. It is dissipated and it interacts with currents and with, of course, with the topography. And so this is what we are interested in. So the question is, what does this model solve? Before the question, I show you. So I show you here the climatology, meaning the average along a year of this fluctuation that you were showing. For instance, here you see that during the winter in the northern hemisphere, you have lots of waves. You have much less during the summer, and this is the other way around in the southern hemisphere. So we are interested in statistical quantities, both here for the climatology, but even the significant wave height itself is a statistical quantity, as you can understand. Okay, so what does this model solve actually? So here what we want to describe is something like the energy of the wave field or the wave action. And so if the systems would be homogeneous, we would solve, for instance, the wave energy spectrum. So here the system is not homogeneous, it is inhomogeneous. So we need to have a notion of something like the local energy spectrum. Okay, so I give you here the mathematical things we solve. For this, I describe the case of a nonlinear Schrödinger equation, which is not valid for the ocean, but just because it's simpler and you will understand very easily. So here you have a nonlinear Schrödinger equation. So I will use this parameter, mu and epsilon, that will both be small in an asymptotic limit. Mu will measure a difference between the typical wavelength and the scale at which I will look the phenomena, and epsilon will measure a small nonlinearity. And so they will scale together to go to 0. So here I use the Wigner distribution, which is the average of the local spectrum. So you take the field, at some points you make a shift in space. Here there is a plus, here there is a minus, and you see I scale it with what I need for later use, and then you multiply by, you make the Fourier transform. Okay, so this is just the Fourier transform of the 2 points correlation function, but as you can see, it will depend on x, okay, locally. Okay, so this is called the Wigner distribution. And then from the Wigner distribution, you can compute the local energy of the wave field and the local action of the wave field. And so for this specific problem, when you take the limit where mu goes to 0 with epsilon is square root of mu, then there is a classical result, which is called kinetic theory. It was written by theoretical physicists probably since the 30s. And here you see publication by mathematician colleagues which prove the validity of this. And then you get a kinetic equation that describes the evolution of n. So here you have the group velocity that transport this Wigner distribution. And here you have a nonlinear part, which is called the nonlinearity of the kinetic theory that describe how wave interacts. So here you have what are called 4 waves interaction, 2 incoming waves that interact with 2 outgoing waves. And so this is a classical piece of theoretical physics. And so this is actually what the numerical model solve. So here you have, it's exactly the same. Here I have just added the current velocity. You have the group velocity. So here you have a nonlinear transport that I just explained before. And on top of this, you have effective dissipation and wind forcing, which are put on top of this effectively. So the question we addressed is, what is the stochastic effects here? When this wave interact, there is this mean effect, which is given by the classical theory, but what is the, on top of this, you have stochasticity, which is due to nonlinearity in the interaction. And so what we did is to, rather than looking at the Wigner function, we looked at the empirical Wigner function. So you see it's the same as before, except that I don't have the average anymore here. And so this quantity is fluctuating now. There is no average. And so we ask, what is the statistics of this fluctuating quantity? And so something we derived with postdocs and a few colleagues, for instance, with Gregory Yink and with Yuhei Onuki. Most of the work has been done by Jules Guyot, a postdoc working with me, is to look at the probability that this fluctuating quantity is equal to some n, and then we show that there is a large deviation principle where you have exponential of minus the small parameter, the inverse of the small parameter, and then there is an action, and this action is related to some Hamiltonian, and then we computed the Hamiltonian, and so with this we can describe the full statistics of the fluctuation of this wave turbulence, while assuming actually that we are in the correct limit for the kinetic theory. And so from this, we can both describe the typical fluctuation, so it gives us this random term that was missing, but we can also use it to describe very rare fluctuation. So for instance, if you are interested to study rogue waves, some events that appear very rarely, then you can try to see whether this might be relevant or not. Okay, so this is an example. So I did that with some of my students and postdocs for several other cases, and so we applied it to several the classical kinetic theory, plasma, systems with long-range interaction, weak turbulence. This is what I just showed you. Okay, so to derive this kind of effective theory through a large deviation principle. Okay, so the conclusion here is that we have derived the stochastic Hamiltonian that characterize the path large deviation for this stochastic field theory, and so it describes in an effective way all the statistics of this wave field. There are strong limitations. We have assumed that we are in the kinetic limit regime, which is sometimes correct, but not always correct. And then, actually, we have assumed that the nonlinearity is not too large, and this is actually for real application. This is probably not often verified, and so there are strong limitations to this, but still it is an interesting piece of theoretical physics that will be useful. Okay, so now this is interesting from the point of view of theoretical physicists, but this is a bit far from real application to the climate urgency. So now I want to show you other problems for which it will be more, the point will be more to use computation and to use the tools of statistical physics to improve the way we compute rare events. So the subject here is rare event simulation and machine learning for predicting extreme heat waves and renewable energy production. So I will begin by extreme heat waves. So here you see a classical movie from NASA. You may have seen it. It's very nice and old and famous. And so what you see here is the speed of the wind on the upper troposphere at a height of about 10 kilometers. And so the red value corresponds to speed that can be up to 30 or 40 meters per second. And so you see that when you look at the fluid mechanics of the atmosphere, like this, it is completely dominated by this red ribbon that goes all around the planet, which is called the jet stream. So the flow is actually self-organized. So it is a jet, just in the sense of fluid mechanics. You have a very strong concentration of momentum along this jet. So you see it has a strong fluctuation and meandering. So when we study this from a fluid dynamics point of view, those are called Rossby waves, and those Rossby waves are in a quite nonlinear regime. And so you can think of nonlinear waves which are forced by the difference in temperature between the equator and the pole, and they are dissipated by many phenomena, mainly radiative effect. And so you see one of these fluctuation here. So it's directly related to the weather. So when you have, so here, for instance, the flow will go like this. You will have an anticyclone here, and the weather will be very nice. Here, on the opposite, the flow will go like this. Here, you will have a depression and a cyclone. So, and this will be associated with descending air here and ascending air there. And here you will have rain and bad weather. So what will be an heat wave? It will be when one of these meanders might, for some reason, become stationary in the reference frame of the planet, and then you will have this anticyclonic situation for an extremely long time. And so this will create heat waves. So this could occur just because the phase speed of the wave at some points will go to zero for some dynamical reason, or maybe because you might have wave breaking, or because of some other physical phenomena. So this picture comes from a weather model that makes data assimilation. So we use climate model, which are a bit less precise than this one, but reproduce fairly well the dynamics. Okay, so I am interested in long-lasting summer heat wave, and so I use this is the 2-meter temperature. So it depends on space and time. So I will average over space, over an area that is typically at what we call the synoptic scale, thousands of kilometers. So for instance, we studied this area, for instance, Europe or France. And then we average over time. And so as I told you before, what matters for us is when this time average is long. So capital T here could be a week, a few weeks, a month, or a full season. Okay, so we use the best available climate model, the one that are used by in the CEMIP experiments that are described much in the IPCC report. And so we also use a model which run faster than those, but for development purposes. Okay, so I won't go into the detail. I will show you just the result. So we use a rare event algorithm, not the one I described before, another one. I will not go into the detail. I chose the other one because it was simpler to explain today. And so here you see one of the results. So this is the return time, so in years. So you see the amplitude of the heat waves. So the amplitude of the heat waves here is just the temperature, the surface temperature anomaly, meaning the difference with the average and with a time average of 90 days. And so here you see a time in years. So you should interpret these curves as the inverse of a frequency. So for instance, here you see 1,000. And so you see that heat wave that comes back every 1,000 years on average will have an amplitude of a bit less than 2 degrees. And so this return time plot is typically what is needed for the purpose of studying risk, because it gives you the probability for a given risk, or the risk for a given probability. So with the climate model, we made a 1,000-year simulation, and we got the black curve. And so with the same climate model, with the same numerical cost, we made these red curves, which allow us to go towards, with a 1,000 years of simulation, to study events that have a return time which is much longer. Okay, so the point is that at a fixed numerical cost, we can study events which are several orders of magnitude more rare, and this is what matters for our application. So here I show you a bit the same thing, but differently. Here you see the numbers of heat waves we get with 1,000 years of simulation. So this is a parameter that we can tune in the algorithm. I don't explain the detail. When this parameter is 0, we just have the model. So the model without algorithm, we have one heat wave with a 1,000-year return time, and we have 20 heat waves with a 25-year return time. And when k is about 300, here you see that we have many more heat waves at the same numerical cost. And so the key here is that we get several hundreds more heat waves for a fixed return time. Okay, so we have a much better statistics. So with this, we studied then the heat waves from the point of view of fluid mechanics, the turbulence of these waves, and also from the point of view of the impact. And so here, for instance, you see the spectrum. So you see the climatology, meaning the spectrum for typical fluctuation. So here you see the wave numbers and the period in day. And so this measures the energy of these waves, of these non-linear Rossby waves. And so you see there are waves at any landscape between 1 and a season. So any time scale between 1 day and a season, and any wave number between 1, which is the planetary scale, and 10, which means 10 oscillations around the planet. And so here you see here we condition on the fact of having extreme 30-day heat wave. And so you see there is a bump here that was not present there. And so this is an unusual quasi-stationary pattern. And then you have a gap, and then this has not changed much. So what's happening here is that during this period of extreme long-lasting heat waves, you have a quasi-stationary wave that comes, which is not present usually. So in order to better see this quasi-stationary wave, what we have done is to make what we call an extreme teleconnection pattern, where you see a map which is conditioned on the fact that this time average is extreme. Yeah. And so you see, I just describe the color, which is the temperature. So this was the study of heat waves over Scandinavia. So you see that it is hot over Scandinavia by definition, because we condition of being hot over Scandinavia. But when it is hot over Scandinavia, you see that it is also very hot over Northern America and Eastern Asia, and it is cold over Greenland and over Russia. And so you have a connection, teleconnection at the global scale between the extremes here over Northern Europe and elsewhere. So it's amazing that we have this global teleconnection. Actually, if you think that it is a wave which is at a planetary scale, it's not so amazing. It's just that you have selected a specific pattern for these waves which correspond to this extreme. And so this is this wavy nature that explains this teleconnection. And so this was published in our first paper in PNAS in 2018. And you see here that the same year, 6 months later of the publication, there was actually heat waves over Scandinavia. And so you see the observation here. It's not directly the observation, it's what are called reanalyzed data set, ERA5. And so you see that it was extremely hot over Scandinavia. And you see that the pattern is very similar. So here we have an average over many examples. Here it's a single realization in the real world. And so you see that the pattern is quite similar. Okay, so it was important to get the rare event simulation to be able to do this pattern. But you see that actually the pattern is realized in the real life. So recently we decided, so we have done much more, but I won't go into the detail today. So recently we decided to study heat waves elsewhere in the world because of their impact. So this is a paper by not by us, but by some colleagues in 2018 that were showing the maximum wet bulb temperature with some scenario in 2017. So it is here you have 100th percentile, so it means that you have temperature higher than what is shown in the map here 3 days a year. So the red part are temperature of the order of 31, 32 degrees. So the wet bulb temperature is a temperature which takes into account of the humidity. So it's basically the temperature of a thermometer if you cover it by something which is wet. So because of the flux due to evaporation, the temperature inside is lower than the temperature outside. And so this is the way we work to physiologically to keep at a lower temperature, even in the temperature outside is large. So when we reach this temperature, basically, most probably it will be extremely challenging to stay alive outside for more than a few tenths of minutes of 1 hour. And so basically this tells you that possibly in all this area of the world here, it might become impossible to live during this situation, during this several years a day. And so this is a key challenge. So you see it would be in 2017 with this scenario. So hopefully we will never see this scenario. With the current mitigation strategy, we are already away from this extreme scenario. But still, it is very important to study whether this might happen and what is the very low probability that we can see this already in present climate or in future climate with less extreme scenario. And so we applied the same rare event simulation with Clément Lepriol and Joy Montero and Indian colleagues. And so you see here the teleconnection pattern for heat waves that occurs on the west of the sub-Indian continent, Pakistan, and the west of India. And so you see that there is also a global teleconnection pattern, and you see here the comparison between the algorithm and an extremely long control run in a climate model that run faster. So recently we decided to apply this also to extreme of renewable energy production. So you might know that for mitigation purpose, most of the problems comes from the energy. About 70% of greenhouse gases emission are from the energy sector. And so we have to change the way we produce and consume energy all over the world. And so in scenario for this, in the IPCC, the main solution goes for renewable energy, and the only current available technology for this are wind and solar power. And so, for instance, in the prospective scenario for Europe, we might have up to 70 or 80% of renewable energy on the electric sector by 2050. And so then we have several challenges. So one of the challenges is that this renewable energy production are intermittent. And so then we have to adapt the system for this. And so there is no very hope that this is feasible with not too much difficulty. But still, for the resilience of the electric system, we need to understand extremely well the very rare events for which we will have a very low production and a very high demand. For instance, a cold winter with low wind and a low value of solar in the southern Europe. And so this, then we use, and if you think about it, it is a climate problem because everything is related to the weather and the climate. And so we we use exactly the same tool as for studying heat waves. The problem from a scientific point of view are very similar. And so we use a production model for wind, solar, and a demand model also. And then we were studying extremes. So again, I won't go into the detail because I don't have time, but this is the work of Bastien Cosian that finished his PhD 1 year ago. And so you see here we also use relevant simulation, and you see here the teleconnection pattern that corresponds to events with 1,000 years return time for an extreme of residual load. And so currently I am working in a framework program between IPSL. The IPSL is the Federation of Labs that work on climate in Paris area, and the RTE, which is the French network. RTE is dealing with managing the grid at the national scale in France, and has the goal for the French state to study this perspective. Okay, so the conclusion is that we can use relevant simulation to gather an amazing statistic for extreme heat waves with Plazine and CSM. So the dynamical mechanism is the birth of quasi-stationary non-zonal global patterns. And so this methodology can be used to study the resilience of the electric systems and the extremes of renewable energy production. So we also studied abrupt climate change, but I will not discuss it today. And currently, we study rare event for studying climate tipping point with several colleagues all over Europe. And we try to go towards using the same family of algorithms to study tipping points. So thank you for your attention.